Welcome back to this course on polymer chemistry, and in this 18th lecture we will continue our discussion on ionic chain polymerization, and in this particular we will discuss the leftover discussion on the termination reaction in cationic chain polymerization. We will also discuss the kinetics and energetics of cationic chain polymerization, and then move to anionic chain polymerization, talk about the features of anionic polymerization, and then like the cationic chain polymerization, talk about different ways of initiation and propagation and termination reactions, and briefly we will touch upon the energetics of this anionic chain polymerization, and then at the end we will talk about this a few practical considerations for ionic chain polymerization, both cationic and anionic. Now, let us just quickly recap what we covered in last lecture on ionic chain polymerization. We talked about general features of or the characteristics of ion chain polymerization and its comparison with radical polymerization. We talked about selectivity of the monomers, we talked about the importance of solvent polarity in case of ionic polymerization. We talked about the nature of reactions, very fast reaction, and we also talked about the inherent difference in the termination reactions between radical chain polymerization and ionic chain polymerization. We talked about cationic chain polymerization in particular detail, where we talked about different types of initiation reactions and then propagation, and we just initiated discussion on termination. And as we discussed that in case of both cationic and anionic polymerization, this bimolecular reactions between these propagating species is forbidden. So, termination is not done that way. Typically the termination happens in by the chain transfer, and there are several possibilities of chain transfer reaction in case of cationic chain polymerization, and we just started giving examples with chain transfer with monomeric species. And what we will do, we will just begin our discussion in this lecture from that page. We were discussing in this last lecture the termination by beta proton transfer to different species, and we gave examples of the transfer reaction with monomer, and just note the rate constant we are giving, and with the same rate constant, this same notation what we use for radical chain polymerization, KTRM. And as I said that there could be two possible double bond in case of this monomers like isobutylene alpha methyl styrene, but for the examples monomers like styrene, it will be only one double bond possible, because in case of styrene you have only one possibilities of beta transfer. Now, let us talk about other possibilities. In this case we talked about chain transfer to counterion, and these are basically similar as in the case of transfer to monomer. So, I am just going through quickly these different types of chain transfer. Here the proton is transferred to the counterion itself. So, you get a dead polymer plus a species as in the case of the transfer to the monomer, and in like in monomer case, the resulting species out of or as a result of chain transfer reaction is same as the initiating species. You remember, if you recall this initiating species for this reaction of polymerization of isobutylene by BF3 plus water, this was the initiating species. So, what happened is, in spite of this chain transfer reaction, the rate of polymerization does not slow down, because this has the same reactivity with the existing kinetic chain. Only thing happens because of this chain termination or chain transfer, the molecular weight actually get reduced. Similarly, in this case, this can again reinitiate a cationic polymerization. So, rate does not get influenced much, whereas the molecular weight get drops, and this is again using the same examples we are showing the chain transfer to counter ion. Chain transfer to polymer is possible, and for example, this is a styrene polymerization, cationic polymerization. In this case, intramolecular proton transfer is possible, which actually gives you a dead polymer chain and again initiator co-initiator complex. And if intermolecular chain transfer happen, chain transfer to polymer happens, then you get a branched chain, or you get branched polymer. So, these are very similar to the reactions we discussed in case of chain radical chain polymerization. Chain transfer also can be possible to the other substance, whether it is present as impurities or you have added deliberately as a chain transfer agent to control the molecular weight. For examples, this is generic structure of the chain transfer agent, which could be water, alcohols, ester, acids or anhydride, etc., and it can participate in the chain transfer reaction and giving away new catalyst co-catalyst complex, which again can reinitiate a cationic chain polymerization. So, again this reduces the molecular weight of the cationic chain polymerization. Now, there is one more terminations is possible, which is not a transfer reaction, which is basically in true sense which is a termination reaction, where this counter ion and this ionic species, the cationic property can species combine and to form a covalent bond. For example, for generic expression we are using, it can be shown here, and the examples of isobutyl polymerization with BF3 and water, you can write termination reaction like this. Now, in this case it is a true termination reaction, because here you are not forming anything else which can restart the or reinitiate the polymerization. As you know, in absence of water, this cannot initiate the chain by itself. So, this is in that sense not a transfer reaction, and it is a in true sense a termination reactions, and you can just note down and the example of this termination reaction. Now, there could be some reagents present, like in case of radical chain polymerizations, where this reagent actually can slow down the cationic chain polymerization considerably. So, they can act as a inhibitor or retarder in case of cationic chain polymerization, like we talked about different retarder or inhibitors like benzoquinone or hydroquinone in case of radical chain polymerization. In this case also there could be other reagents possible, which if you add or present as impurities, it can retard or inhibit the chain polymerization, cationic chain polymerization. For examples, amines or triaryls or trialkyl phosphates or thiophenes, they can actually act as an inhibitor. For example, if you take specific examples of amines, they can react with this propagating species and form a cation complex such in this case this cationic species is very stable and they are non-reactive towards the monomer. So, once this is formed, this cannot reinitiate or this cannot actually take part in further propagation reactions, which means this chain actually gets inhibited by this type of reaction. So, like radical chain polymerization, there are molecules or reagents which you can or maybe undesirably they are present in they can be present in cationic chain polymerization. So, we just talked about different possible probabilities of initiation reactions, propagation reactions and types of termination reactions possible in case of cationic chain polymerization. Now, let us talk about the kinetics of or get some deduce kinetic expression in case of cationic chain polymerization. Again we will consider, like said, we will consider the most important example of the initiation reaction, and we consider the generic expression minus and so these are the two steps consist make the initiation reactions, and as I mentioned earlier that this is your rate determining step. So, the rate constant for this reaction is considered. So, if I write expression for rate of initiation, it would be K I concentration of this species y plus I z minus and concentration of monomer. As I mentioned earlier that here in the rate expression for initiation reactions this monomer is appearing, where in case of radical chain polymerization monomers was not present in terms of in the rate expression of the initiation reaction. Now, if you get the value for this from this equilibrium, we can write K I y z m. Okay. Let us write the propagation step. Write this generic expression so rate of polymerization Rp is given by Kp, concentration of and the monomer. Termination reaction. Now, let us consider the true termination reactions, which is the combination of the cationic propagating species with the counter ion. We are not considering for this kinetic expression the other transfer reaction. So, we can write Kt gives us Iz. So, RT rate of termination is given by the concentration of now for simplicity just write like earlier case where in case of radical polymerization let us write this only M plus. So, this is the summation of concentration of all the cationic species present in the reaction medium M1, M2, M3 and so on. So, for simplicity we are just writing omitting this subscript and writing this M plus. So, again this is the summation of the concentration of the all the cationic species propagating species present in the medium. Now, at steady state we can equate Ri and Rt to get the concentration of like in case of we have used similar approach in case of radical chain polymerization. So, we get this. So, Rp similarly can be obtained Kp I Yz. Now, here this rate of polymerization is depend on the square of this monomer concentration, where in case of radical polymerization if you remember it was related to the concentration of monomer. That is because this monomer is appearing in the rate expression of the initiation reaction as well in case of ionic polymerization, where in case of radical polymerization this monomer was absent in the initiation reaction. So, I can write the degree of polymerization like Rpa by Rt, which gives Kp m by Kt. Now, similarly if transfer reactions happen, I can write in Rp plus summation of all the chain terminating reactions. So, R Ts plus R transfer monomer plus R transfer solvent and so on. So, we can just simply write as Kp m Kt Kts chain transfer to the counter ion, chain transfer to the monomer and chain transfer to the solvent or any other substance, or you can add if there are other chain transfer reactions present. So, similarly like in case of chain polymerization, we can write this MAO expression. This is x n bar 0 is the degree of number of average degrees of polymerization in absence of any chain transfer reaction. So, if only transfer possible to monomer, then we can write x n bar is plus C m. Okay, so, the more the transfer reaction, obviously the average degrees of polymerization comes down. So, as same sort of discussion we can have what we had for the Maillard reaction chain radical polymerization. So, increasing the solvent concentration which is taking part in the chain transfer reaction, or increasing the monomer concentration, or similar things we can discuss exactly like the chain transfer reactions for radical polymerization. So, let us talk about the energetics, which means that the effect of temperature on the reaction rate and molecular weight. Like in case of radical polymerization, if you just recollect this this is the expression for your Rp, rate of polymerization, and this is the expression for your average degrees of polymerization. So, we can write similarly activation energy for reaction E I initiation plus E for propagation minus termination, and E x n was 0 in absence of any chain transfer reagent. We can write this. Okay. Now, typically in case of cationic polymerization, both E I and E P are lower than the termination activation energy, as can be justified because that bimolecular termination is not possible, and E P values are typically from minus 20 to 40 kilojoule per mole, which also depends on the monomer structure. For same monomers, the activation energy or propagation will of course depend on the initiator or co-initiator and the solvent. For example, let us this E P values is around no, E P values comes around say 20 to, let us go back, and this E R value, it can be positive or negative, and the values is typically from minus 20 to 40 kilojoule per mole. So, if I want to find out the effect of rate of cationic chain polymerization with temperature, we get this E R like earlier case, and depending upon the value or sign of E R, you can tell whether the reaction rate will increase with temperature or not. If this E R is negative, then R P goes up with temperature goes down. If it is positive, then R P goes up with increase in temperature. Now, do not confuse that activation energy for reaction is negative. No single reaction can have a negative activation energy. The activation energy for reaction in cationic chain polymerization could be negative, that is because it is a combination of activation energy for initiation, propagation and termination reaction, and if the activation energy for the termination is higher than the combination of activation energy of initiation plus propagation, then it would become negative. So, the rate increases with the temperature. If this is negative, if it is positive, then the rate of reaction increases with the temperature. Similarly, you can write the expression for the molecular weight x n 0 in absence of chain termination reaction. Now, as we just said that E p is less than E t in most cases, in most general cases. So, this is negative, which means that x n 0 goes up with decrease in temperature. So, the molecular weight always decreases, molecular weight always goes up if you decrease the temperature of the reaction. That is why cationic polymerization, botanic chain polymerization is most cases performed in a subambient or sub-zero temperature. Now, if you consider this chain transfer reaction or chain transfer constant, C is say for chain transfer to the monomer is given by KTR this. So, dln C by dt will be given by ETR minus EP by RT square. Now, typically E transfer is higher than EP. So, which means that with increase in decrease in temperature, C also goes down, which means x n goes up. So, what we found that even for the reactions where transfer reaction is absent, if we decrease the temperature, the molecular weight goes up. The cases where transfer reaction present, the transfer constant goes down with decrease in temperature, as a result the molecular weight goes up. So, for cationic chain polymerization, no matter whether chain transfer reaction is present or not, you always end up having higher molecular weight if you decrease the temperature. Now, whether that also simultaneously increases the rate of polymerization, that depends on the value of the activation energy for reactions. If it is negative, then with decreasing temperature you get increase in polymerization rate, but if it is positive, then with decreasing temperature you get reduction in the polymerization rate. Now, if you can do reactions where you do not have these side reactions or this chain transfer reaction, then you can keep these propagating cations, cationic propagating chains alive, and you can get living cationic polymerization. Now, we are not going to in details about the living cationic polymerization or in this course, but there are, though it is very difficult in case of cationic polymerization, in a very careful manner, if you can do reactions where you reduce or minimize the chain transfer reaction and the side reactions, then there is a possibility that you can get a leaving chain polymerization. Now, this cationic chain polymerization can be utilized to synthesize tetracyclic polymers as well, where tetracyclic term means low molecular weight, typically less than or 20 K molecular weight, with a functional group at the end, which can be utilized for further reactions. For example, we take this reaction, general reaction, so you can consider this reaction of this with isobutylene, and you get a propagating chain like this. Which can again react with this alkyl halide. Now, this chloride can be utilized and reacted to form several types of N groups, say like NCO or CH2H or allylic groups or something like that. So, by this way you can terminate a cationic chain polymers with the desired molecule, in this case alkyl halide, and you can make functional groups at the end, which you can utilize to form different functional groups, and then further reactions possible in that functional groups. Sometimes in cationic polymerization, you also, if you do a characterization of the polymers you gained at the end of cationic chain polymerization, you might get, or you might see there is a bimodal distribution of the molecular weights. Now, in that case what might have happened, that there could be possibility of simultaneously present of two different types of these ionic associated counter ions, and as we know that the reactivities of the free counter ions and or the solvent separated counter ions are much different than tight ion pairs. If they are present in significant amount, then they will propagate in a different rate, that might lead to different set of molecular weights, which you might results in a bimodal type distribution of this resulting polymers. Now, what are the practical considerations in case of say cationic chain polymerization? For a successful cationic chain polymerization, as we just discussed, usually done at a temperature less than say 0 degree centigrade, because as we have seen that with reducing temperature you can get a high molecular weight, or molecular weight increases with decreasing temperature. Now, you have to maintain moisture free environment, and if you actually using H2 as a co-catalyst, then you should add H2O in the stoichiometric amount with respect to the catalyst, because if moisture or H2 is present in excess than what you desire as a co-catalyst, then the cationic propagating species will react immediately with the water molecule and terminate the polymerization or propagating chain. And for the same reason, the purity of purity of monomers are very important. If there are impurities which can undergo side reaction or do chain transfer reactions, then the molecular buildup is a problem, and these reactions, because oxygen is also a very killer for this cationic polymerization, inner atmosphere is needed, and for that the nitrogen or the argon gas which are used for creating the inner atmosphere, they must be purified very rigorously. And because these reactions are very fast reaction, sometimes it happens in seconds. The cationic chain reactions, actually you can make arrangement to perform the reaction. You might have to arrange or purify the monomer and the gas, nitrogen or argon, and you have to make this your container or the reactor moisture free. For that you may spend lot of time, but the reaction happens very quickly within seconds, and because it happens so quickly, it generates lot of heat, and sometimes this heat management is also a problem. Now, for all these reasons, as I said in the very beginning, that doing or carrying out this cationic chain polymerization in a large scale industrial scenario is very difficult. That is why this cationic chain polymers are not practiced commercially for many monomers. The only monomers which are synthesized in commercial scale is butyl rubber, which is basically copolymer of isobutylene, the example of which we gave many times in this lecture, and small quantities of isoprene, and this is done at very low temperature, 90 degrees centigrade, with aluminum chloride catalyst and in chlorinated solvent. Now, this butyl rubber remain flexible at low temperature like minus 50 degree. So, they are used in the inner tubes of tires, engine or auto body mounts, and electrical cable insulator, protective gloves, etc., and some pharmaceutical stoppers. So, this is the only polymers or copolymers used which utilized this cationic chain polymerization commercially. Now, let us move to the next topic of anionic chain polymerization. Now, it is similar to cationic, but there are some significant differences as well. One difference is that the difference in the activity of these different ion pairs is much strong in case of anionic polymers, anionic chain reactions. Which means that reactivity of free ion, the difference in reactivity of free ion pair with say a tight ion pair is much more important in case of anionic chain polymerization than in case of cationic chain polymerization. There could be there are other differences as well, and this is not as temperature sensitive as cationic polymerization, and generally ER, the activation of reagents is positive, small positive. So, if you decrease temperature, rate of reaction goes down. So, generally reactions are done at ambient temperature or maybe slightly higher than at ambient temperature. The solvent is very important, even more in case of anionic polymerization. The solvents are mainly used is aliphatic or aromatic hydrocarbons. You cannot use halogenated solvent which were suitable for cationic polymerization, because they are facile nucleophilic substitution reactions with the carbon ions, and other polar solvents like alcohols, or ketones, esters also cannot be used, as well as H2O cannot be used, because the same reason of cationic, because they can very quickly react with the carbanionic propagating species and terminate the chain reaction. Now, other difference of anionic polymerization with cationic polymerization is this possibility of the transfer reaction. Now, in case of cationic, we have seen that in case of cationic we have seen very fissile beta proton transfer or elimination reaction happening for this transfer reaction, where in case of anionic polymerization you require beta hydride elimination for those transfer reactions with monomer, solvent and counter and all these things to happen. Now, hydride elimination is not a very easy thing. So, this extent of transfer reaction for anionic polymerization is much less compared to cationic polymerization, which means that the side reactions and the chain transfer reactions are very less if you have a very pure monomer and moisture free environment. That is why leaving anionic polymerization is comparatively easier than cationic polymerization, because in case of cationic polymerization these transfer reactions are very common and facile, where in case of anionic this transfer reaction which require beta hydride elimination, which is not a easy thing. So, leaving anionic polymerization are quite often easily achieved compared to a leaving cationic polymerization. Now, let us talk about the 3 steps: initiation in case of anionic polymerization, most important is using alkyl lithium. For example, I have this butyl lithium which can react with monomers, giving rise to Now, these alkyl lithiums are required to make these initiators soluble in organic solvent or soluble in non-polar solvent. As we have seen earlier or we have discussed earlier, that anionic polymers are typically done at aliphatic hydrocarbons or aromatic hydrocarbons. Other initiations possible by electron transfer. For example, reaction between sodium and naphthalene. Now, this can react with one more of same molecules. Okay, let us this is another possibility where sodium can react with naphthalene by electron transfer. You can generate a anionic species which can initiate, it can react with the monomer to initiate the chains. If I write the chain initiation reaction for that electron transfer reaction, it can react with the monomer to initiate the chain. Say why is styrene, we are talking about styrene polymerization here. This can resonate. Now, this can dimerize. So, this is example of how initiation is done with electron transfer. In this case, we took example of sodium and naphthalene, and in this case you can see this final or the initiating chain initiating species formed is this, which actually can extend or propagate from both the sides. So, you can have reactions happening in both the propagation happening in both the sides. If we talk about the this propagation of this butyl lithium reaction, this butyl lithium, which is very common and more important. Let me write the propagation reaction for that, generic propagation reaction. And if you talk about the propagation reaction of this this species, then you can write propagation reaction this plus So, basically this, as I said, that it can propagate from both the sides. So, this is what a propagation reaction will generically look like. Now, these are the examples where you do not have a inherent termination reaction. In both these cases, this initiation by alkyl lithium and also by this electron transfer, you do not have any inherent termination reaction. So, the reaction can proceed without a termination reaction and the reaction or the propagating chain can remain living. But if you want to stop the reaction for whatever reason, then you can add a reagent which could be alcohol or water, which can actually react immediately with this active anionic carbon anionic chain end and stop the reactions. So, termination reaction, if you can add H2O or say methanol or any other alcohol, and which can terminate this reaction very quickly. Now, this is not sufficiently nucleophilic to reinitiate a chain polymerization, which also mean that if you have H2 present, undesired H2 present during the polymerization medium, in the polymerization medium, then it has a very detrimental effect in terms of molecular weight buildup, because if there are trace amount of H2 also, this will immediately react with the propagating carbon and anionic end and stop the reaction immediately, which will have very detrimental effect in terms of building molecular weight. Now, there, as I said, there are not inherent termination reactions for this type of initiation or propagation reaction, but some polar monomers can have side reactions present, which actually can determine or be detrimental for your molecular weight buildup. And there are other possible initiation reactions which we will discuss in the next lecture, where inherently there could be termination reactions possible. So, what we have done in this lecture, we have talked about general features of anionic polymerization. Anionic polymerizations, as I said, that it is much more solvent dependent compared to cationic chain polymerization, and the inherent termination reactions, as in the case of cationic polymerization by beta proton elimination, in that cationic polymerization case is not present here, because beta hydride elimination is difficult. So, it is always comparatively easy to carry out leaving anionic polymerization than leaving cationic polymerization. And we talked about different initiations possibilities of this anionic polymerization, and most important of these is using alkyl lithium, and the other possibility is using these electron transfer reactions, examples given sodium and naphthalene. And as we seen this propagation step, that termination is not present. So, if one required to terminate the chain, you can add externally this H2O or alcohol to terminate the chain, but there are some polar monomers like methyl methacrylate or methyl vinyl ketone which can undergo side reaction, which actually restrict the molecular weight build up. In next lecture, what we will we will start giving that example of the side reactions in case of the polar monomers like methyl methacrylate or acrylonitrile or methyl vinyl or methyl ketones, where the side, because of the side reactions, the molecular buildup is difficult. And also we gave example of other type of initiation reactions where there could be inherent termination reaction. And in the next lecture, we will also consider the little bit of energetics, how the temperature affect the anionic polymerization and how the molecular distribution is in case of anionic chain polymerization, and how to get the molecular weight from the initial monomer and initiator ratio. So, with this I stop this lecture, and in the next lecture I will continue with this anionic chain polymerization, and we will start the other type of polymerization in the second half or later half of the next lecture.